Welcome everyone. Let's see what is the Dining Philosophers Problem. The Dining Philosophers Problem is a classic synchronization and concurrency problem in computer science and operating systems. It illustrates issues related to resource allocation and deadlock prevention in a multiprocess environment. It is an example problem often used in concurrent algorithm design to illustrate synchronization issues and techniques for resolving them. Five philosophers dine together at the same table. Each philosopher has his own plate at the table. There is a fork between each plate. The dish which is served has to be eaten with two forks. Each philosopher can only alternatively think and eat. Moreover, a philosopher can only eat his food when he has both a left and right fork. Thus, two forks will only be available when his two nearest neighbors are thinking, not eating. After an individual philosopher finishes eating, he will put down both forks. The problem is how to design a concurrent algorithm such that no philosopher will starve. That is, each can forever continue to alternate between eating and thinking, assuming that no philosopher can know when others may want to eat or think. And a point to be noted is there are many variations of this problem, such as instead of a fork, a chopstick can be used, and instead of noodles, a rice bowl can be used. But the logic and the solution of the problem will be same. The problem was designed to illustrate the challenges of avoiding deadlock, a system state in which no progress is possible. To see that a proper solution to this problem is not obvious, consider a proposal in which each philosopher is instructed to behave as follows. Think unless the left focus is available. When it is, pick it up. Think unless the right focus is available. When it is available, then pick it up. When both forks are held, eat for a fixed amount of time. Put the left fork down. Put the right fork down. Repeat from the beginning. However, each philosopher will think for an undetermined amount of time and may end up holding a left fork, thinking, staring at the right side of the plate, unable to eat because there is no right fork until he starves.
The Dining Philosophers Problem highlights several challenges in concurrent programming, which includes deadlock, resource contention, starvation, complexity, and scalability. Now let us see about deadlock. What if every philosopher sits down about the same time and picks up his left chopstick as shown in the following figure? In this case, all chopsticks are locked and none of the philosophers can successfully lock his right chopstick. As a result, we have circular waiting. What is circular waiting? That is, every philosopher waits for his right chopstick that is currently being locked by his right neighbor, and hence a deadlock occurs in this case. Now let us see about resource contention. Multiple philosophers may compete for the same forks, causing inefficiency and it lead to slow performance. What is starvation? Let us imagine that two philosophers are fast thinkers and fast eaters. They think fast and get hungry fast. Then they sit down in opposite chairs as shown below. Because they are so fast, it is possible that they can lock their chopsticks and eat. After finish eating, and before their neighbors can lock the chopsticks and eat, they come back again and lock the chopsticks and eat. In this case, the other three philosophers, even though they have been sitting for a long time, they have no chance to eat. This situation is called as starvation. Note that it is not a deadlock because there is no circular waiting and every philosopher has a chance to eat. Complexity. Implementing a solution to ensure fairness, prevent deadlock and avoid contention can be challenging. Scalability. Scaling the problem to accommodate more philosophers or resources can make it even more complex. Solving these issues requires careful synchronization and proper resource management techniques. Here is one possible solution. The image above is a guide to help you completely analyze the problem. Let us assume P0, P1, P2, P3 and P4 represents the 5 philosophers, whereas F0, F1, F2, F3 and F4 represents the 5 folks. Now let us discuss this code. If philosopher P0 wants to eat, it will enter into a philosopher function and perform take fork of I operation. This will hold F naught fork and then it will execute take fork of I plus 1 mod phi. Now this will hold F1 fork because we know that I is equal to 0. Therefore I plus 1 mod phi is equal to 0 plus 1 mod phi, which is equal to 1. Similarly, if a philosopher P1 wishes to eat, it will enter into a philosopher function and perform take fork of I. This holds F1 fork and then it will execute take fork of I plus 1 mod phi. This holds F2 fork because here I is equal to 1. Thus 1 plus 1 mod phi, which is equal to 2 mod phi, which is equal to 2. But practically fork F1 is not available as it has already been taken by philosopher P0. Hence the above code generates problems and produces race conditions in our problem.
To solve this issue, we can use semaphore. Now let's see what is a semaphore. Semaphore is simply a non-negative variable that is shared between threads. A semaphore is a signaling mechanism, and another thread can signal a thread waiting on a semaphore. For process synchronization, it employs two atomic operations, wait and signal. Depending on how it is configured, a semaphore either allows or denies access to the resource. A fork can be picked up by performing a wait operation on the semaphore and released by performing a signal operation on the semaphore. Initially, the elements of the semaphore F0, F1, F2, F3 and F4 are set to 1 since the forks are on the table.
Let us now modify the above code by adding wait and signal operations. We need to initialize a semaphore for each fork on the table. Each semaphore will represent the availability of a fork. In the starting, we will set all semaphores to 1. It shows that all forks are available. Each philosopher will be represented by a separate thread or process. Each philosopher has to follow the same set of steps. These steps include activities such as thinking, attempting to pick forks, eating, releasing forks, and repeating the cycle. Then we will start by thinking or performing any other activity not involving forks. Whenever a philosopher wants to eat, they need to pick the two adjacent forks. To pick a fork, the philosopher attempts to decrement the corresponding semaphore value. If the value of the semaphore is greater than 0, this will show the fork is available. Then philosopher proceeds to pick that fork. Otherwise, if the value of the semaphore is 0, this will show the fork is currently being used by another philosopher. Then philosopher waits until the fork becomes available. Once a philosopher has successfully picked both forks, they can eat for a certain amount of time. After finishing eating, the philosopher releases both forks by incrementing the corresponding semaphore values. Then make forks available for other philosophers to use. The philosopher then goes back to thinking or performing other non-fork related activities. Thank you for watching.